a DIN rail mounting digital timer, but this one's different from the normal ones. It came from eBay, and the listing describes it as TM623 220 volt, I'm guessing it's available on 120 volt as well, programmable astronomical time switch with a latitude longitude display. And it was fairly expensive for a timer like this, but it does have that latitude function which justifies the extra price, £12.21, because, as if that's a high price, because it has that extra functionality that's kind of, unusual to find in these things. So what it means is that instead of just switching on and off at fixed times, that, say for instance you program it to turn on at 9 p.m. at night and off at 5 a.m. in the morning, if you set the astronomical mode, it'll actually adjust those according to the time of year, so it adjusts for the length of the night. And this thing has a couple of odd quirks. Now let me for a start, I'm going to zoom back out. I'm going to bring up the hoppy, and we shall plug the hoppy in and analyse it, because this will give us a clue as to the circuitry inside. So if I plug it into the hoppy says that it's drawing 0.8 watts and 23 milliamps, and the power factor is 0.14. This pretty much suggests that there's a capacitive dropper in there. Okay, I shall unplug it. There's a very, very intriguing feature that I am a bit perplexed by. I can guess what circuitry it is. There's no reset button, in the sense that if it crashes or you want to restore the settings to 0, there's no actual button for that. Oh, there's a little hole here, but it's just a light. There's a button marked R here, but it's not a reset button. To reset it, and it's just the fact it's right next to the mains input terminals here. I'm going to show you this. I'm going to set this to 20 amps. I'm going to put it into the 20 amp probe. I'm going to turn it on. Watch what happens to the display when I short these two terminals here, and watch what happens to the LCD display, if you can actually see that. I shall tilt it up so you can see this. Oh, let's try and do this without blocking. So it went up to over half an amp and the display went out. I reckon, because if I switch this back to volts and I probe in there, I'm getting about 2.83 volts, and if you leave it for a while, that increases. And it's interesting to note that if you plug it into charge, that voltage does also increase. So it's got what I'm guessing is either a couple of nickel metal hydride cells or a lithium battery in there. And it looks from that current that as if, like, to reset it, you basically just short it out and that resets it. It seems a bit wild, but we'll find the circuitry when we go inside. Now, next thing I'm going to do is I'm going to show you how to program this, because the instructions that come with it are kind of, it looks as though they've been copied from various other products and bits have been left in that aren't relevant. But as far as instructions go, it's really not that bad. It is a wee bit sort of auto-translate, but it's okay. It actually gets the message across. It wasn't too hard to work out how to program this, but part of the reason for this video is that I will be showing you right now how to program this. So I'm just going to set this up into something higher to bring it up closer to the camera, and I'm also going to add some lighting. I shall be back in a jiff. So with better lighting for this now, we can continue. So the first button here is marked MD, and that stands for mode. The next button along is R, which apparently stands for recall. Then the next one has a left-hand arrow, and it's called shift, but it's not shift in the sense of shifting between sort of modes as such. It's stepping along what you're setting. And then we've got a down arrow and an up arrow. So the first thing you can set is your latitude and the date. So to do that, you press both these two left-hand buttons. And it displays N30, which is the default setting. That means north 30. If you then press shift, it then lets you select that. And it's displaying L for latitude, and it's also showing the little latitude symbol up there. The latitude here is apparently north 45. So I'm going to set that to 1, 2, 3, 4, 5. No, actually it's not, it's 54. I'm talking crap. It's 54. There, that should be better. And then I'm going to press the shift, and it will go across. The N will start flashing, and all you can choose is south or north latitude. So north latitude it is. Press that again, and it reverts back to that. Now, in this same mode, if I press this button, it lets me set the date. So it's displaying 12/12/2019. It's showing a D for date. Press the select here. It's the day, I think, which is about the 15th today when I'm recording this. And if I then press shift, and it's May when I'm recording this. And then the 19 is flashing for the year, so it's 2020. And shift that again. And if I press this, it should go back to normal mode. Okay, so that's the date and the longitude latitude set. However, to set the times, you have to hold this button down. See how it says lock? You have to hold this button down for 3 seconds. 1, 2, 3, and it unlocks it. Now, to set the time, you press shift. And at the moment, the time is... What is the time? Let me just check that. It's early in the morning. It's 1:41 a.m. That's terrible. Okay, so let's go to 41. 41, shift. And then we're going to scroll up to 1 o'clock in the morning. Oh, it's 1 o'clock in the morning. And shift again, and it does actually let you nudge the seconds up and down, which is quite odd. And then shift again, and that's it, reverted back. At this point, you can then program the times. And if I press this button here, the first time it displays, it's already set one at 9:14. And that's the on time. And if I then increment to the next on time, it's 1:05. And you know what? It must just have this as a default setting, because that is the exact time right at the moment that I've got my outdoor lights set to, because that is the exact hours of darkness here. So it's set, basically, it's set a streetlight mode. However, you can continue. You can press that again, and incidentally, you can just increment backwards and forwards with these up-down buttons. But say, for instance, I wanted to set a second on time of, say, I started in an office or workplace at 9 o'clock in the morning, or I wanted Christmas lights to come on at 9 o'clock in the morning. You can then press select, and you can say, set that for 9 o'clock in the morning. I'll just hold it to do it through. And then if you step across, it's interesting to note, but you want it on at 9 every morning regardless. So see that little latitude symbol? If I press this again, all the digits flash, and at that point you can toggle that on and off. So by toggling the latitude symbol off, that will always come on at 9 o'clock regardless, because that's when people would be turning up for work and they'd see the Christmas lights. So now I can press on to the next mode, which is 2 off, and let's say we turn it off when everybody's going home, so 1700 hours. So I should just do that. This is just as an example, but because, again, we don't want it, if I increment that across, the whole display flashing. If I don't want it turning off, adjusting to the darkness, I'll just press that button. And now that has got the little latitude symbol, which I was toggling on and off there, has gone off, and it will always turn off at that time. If you wish to change settings, you can go back. So you can actually step up and down them. If you wish to remove the second on time I put, all you have to do is press R, and it deletes it. And then the second off time, you can press R and it deletes it as well. And now it will just be displaying the original 2, which was the sort of streetlight mode, on at 9:14, off at 1:05. It's quite interesting. Once you finish setting those, you can just leave it and it will automatically revert back to normal mode. If you press and hold this for about 3 seconds, the mode button, it will lock again, it will revert back to normal mode. The only other thing that's worth mentioning here is that, as with most of these things, there's an override. So at the moment it says auto off. What that means is it's off at the moment, but it's an automatic mode, so it will come on and off for those times. If you press the two outer buttons, that's mode, and the up arrow, you can increment through that. So if I do it once, it displays on, and that is just on continuously 24/7. If I press it again, it says on auto. That means it's on, but at the next automatic off cycle, it will then just step back into automatic mode. I can then press off and it would stay off continually, although don't use this as a means of isolation. But it should stay off continually. And then the last one is off auto, when it's off at the moment, but the next automatic cycle that it comes to when it's supposed to switch on, it will switch back on. Okay, at this point in time, I think we should take this to bits. So the first thing I'm going to do is remove the wires. It's worth mentioning at this point in time that they are rising clamp terminals, which is quite nice. The DIN rail mount facility has two snaps that can go in. So once you've got this in position, you can click these down and it will lock it onto the DIN rail. Other things worthy of note, it's got three terminals down here and it's got a symbol on it that shows the common in the middle, the normally open, which is the main one you'd use, and then normally closed. I did not get a connection to normally closed. We'll explore that inside. Also, it's worth mentioning it's got a plastic cover. I thought that was just film over the LCD, but it actually feels like a hard plastic cover. I scratched it while trying to get the film off it, which did not exist. So I'll put that little plug out the way. And we shall open this. So it's the usual arrangement. It's got the little clips at the side, which are going to be hellish to open, probably. Actually, that wasn't too bad. There we go. Okay. I can actually see looking at this. There's the two connections that are used. The other one has the track there with good separation, I have to say. Let's zoom down that a little bit. It looks as though it's got good separation and fairly chunky tracks, but the other contact is missing, so that is just not used. It's a it's a single pole relay. It's not changeover. The electronics inside, which we shall explore further. There's the module. And it's got three wires going down. It looks very typical. It will have the plus voltage. There's the lithium battery, by the way. It will have the plus voltage, the zero voltage, and it will have the control signal going down to, well, a couple of transistors here. Here's what's almost certainly the capacitive dropper capacitor. A big resistor. A metal oxide varistor by the look of it, across the supply input. It's got a bridge rectifier down there, smoothing capacitor. Looks like a big zener next to the smoothing capacitor, which is a bit annoying. Is that a rechargeable cell? I did see the voltage go up, so I'm guessing it's a rechargeable cell. And then the relay, let's check this out. I'm going to take a picture of this so we can see a bit closer. It says 16 amp 250 volt AC. 16 amp 24 volts DC. The specifications on the unit and the instructions were different. 24 volt DC coil. I don't know if you can see that. Right, tell you what, I'm going to take a picture of this and then we'll reverse engineer it and see what the circuitry is like. Okay, for those of you who want to have a go at reverse engineering at home, here's the first layer. It's the top of the circuit board with all the components on it. And if you want to take a snapshot of that, and then underneath, well, thoroughly scribbled all over, is the flipped image so that all the tracks in the right place for this. Right, let's reverse engineer this. So it has the capacitive dropper. It's a 330 nanofarad capacitor. It's got this inrush limiting resistor, and it's got a metal oxide varistor across the incoming supply as protection. It does have a conventional bridge rectifier, full bridge rectifier, and then a big smoothing capacitor right next to that hot zener diode, which isn't so great. I didn't measure the voltage across that. I should have, because it's a bit odd, the circuitry. Maybe I should measure the voltage across that. Let's measure the voltage across that right now. Is this a good idea? Is this going to end horribly? Where is that connector? Let's just stuff wires in and make sure that I don't put them in the wrong terminals, because if you do, it does apparently connect it straight across this lithium cell and all the circuitry. I wonder how many people have done that they've got the two wrong terminals. They put mains in and it's gone kaboom. So this one is going in here. I should do a better job of mushing those strands in. And this one is going in here. And I think I'll measure across the electrolytic, because it'll be easy to do that. From the back of the circuit board, it should be pretty obvious what connections it is. So I shall just tilt this over and then I shall poke about while this is powered. Excellent. What could possibly go wrong? Oh, like that, basically. Stiff wire. That could go wrong. Right, just remind myself, where is the electrolytic? The electrolytic is about there. Just double check that before I do this and make a terrible mess of things. I could just go across the bridge rectifier as well, couldn't I? Yes, I could. Okay, I may do that. Actually, no. Yes, I can, because it has the zener. Okay, right. It's live. Don't touch it, anybody. You'll die. Let's set it to 200 volts. Let's make sure it's not set to the 20 amp setting. And let's probe about in here. 36 volts. Isn't that just a bit too high? That's weird. Why is it 36 volts? That is strange. That means that zener is going to get very, very hot. And it means that relay is being driven really quite hard. That is strange, even given the other part of the circuitry. I now feel the need to go and take a wee peek underneath and see where's that other bit of circuitry I want to see. I'm going to have to turn the power off and lift it up to finger across and find out where's that other little zener. The other little zener is about, yeah, just bear with me here. Maybe I should have done this beforehand. There is the other little zener diode. Let's just measure the zener diode from the top. It's easier because there's another little zener and it has an odd position in the circuitry. Right, I'm going to measure this and I'm going to guess it's going to be round about just over 4 volts. Let's poke into this live circuitry and see what happens. 3.6 volts. Okay. Oh, I know. You have to. Yeah, just give me a second. I'm going to have to enable the relay because there's something very, very strange in this circuitry. Yeah, I should have been more organized, shouldn't I? It's unplugged at the moment. This is where you have terrible incidents when you're plugging and unplugging. So I'm going to override that to bring it on. Excellent. Let's just get that out the way again. And now let's measure the voltage across that and set it to 20 volts. So this time it's going to be higher because now the relay is active. I want to measure the voltage across the relay. Now, the circuitry is weird in this thing. Very weird. There are some almost like flaws. Yeah, the voltage is 4.13. Then it goes through a diode. I don't know what the voltage drop across the diode is. I think it's that one. It's 0.6, a standard diode. So the rechargeable lithium cell, if it is rechargeable, is not getting too grilled. Right, tell you what, I'm just going to flip this over again, and I'm going to flip this up like that and plug it in again. I want to measure the voltage across that relay. At some point, this is going to go bang. Right, let's measure across the relay. It's 21 volts. Oh, that is so strange. Now I want to measure the voltage across this transistor. 1.5. Oh, do you know what? I wonder if now the relay's on, it's pulling the voltage down across that zener diode. Excuse me, just experimenting here. Yeah, it is. It's pulled it down. That's strange. Okay. I wonder if that's just kind of compensating. It's relying on the impedance of the capacitor here, the dropper capacitor, to actually drop the voltage down. It means it's going to give it a boost, but initially when it powers up. But that's not too bad. What voltage is that capacitor then? Yeah, see, I should have done all this before. It's 100 microfarad at 50 volts. It's amply capable. It's fine. There's nothing really major going on there. Right, tell you what, let's look at the schematic now. I've faffed around for ages. So there's two transistors. One transistor is actually switching the other transistor off when it turns on, and vice versa. Well, not vice versa. When this goes on, that goes off. When this goes off, that goes on. Smooth capacitor, big hot zener diode, which is going to bake that a 0 ohm link. The little zener that is actually giving the charge voltage for this, and a 200 ohm resistor, which is limiting the current to the charge for this. It's very straightforward after that. Here is the schematic. Let's walk over the whole thing. So the incoming supply has the metal oxide resistor across it. That's that little green thing there. Metal oxide resistor. It has this 330 ohm resistor to limit inrush current to protect the circuitry, and then this drop capacitor, which is a nice reassuring little 330 nanofarad. That is the bit you'd change if you wanted to convert this to 120 volts. You'd change that to something like 680 nanofarad, 470 nanofarad, something in the region of double 330. It's got a 1 mega ohm resistor across it, but sneakily it's hidden underneath the capacitor. You can just see the extra pads here for it. Probably an underrated resistor. It's got the discrete bridge rectifier. It's got the smoothing capacitor, which is 100 microfarad, 50 volt, and then it's just that zener. Then it's just basically capping. That was that about, say, 30 volts or something like that. That was quite high. Okay, then it all gets a bit weird. So it's creating another supply to charge the lithium cell here with this zener diode, and then a resistor limit current, and then a diode to protect against reverse charge. That's probably why they've used a standard diode, because it's got less reverse leakage. When you power this up, current flows through this resistor, and if the control circuit, which is, it's got 3 connections, 2 of them are across the lithium battery, and it's got the third connection as the control back. When it pulls that down, it effectively turns this transistor off, so it's pulling to the 0 volt rail, which actually makes sense given that, you know, it's basically a floating control line, because otherwise that it's operating with another higher voltage line, but so the common reference is the 0 volt rail here. So normally, if that control module was off, this transistor would be turned on, and normally this transistor here that turns the relay on would also be turned on by this resistor going trickling current into its base. But when that one is turned on, it actually shunts the base of this one to the 0 volt rail and turns it off. But when the control circuit pulls this to ground, it turns this transistor off, and then the current can flow through this and turn this transistor on. And this is where it's a bit weird. Standard configuration, got a relay coil with a diode across it in reverse parallel, just to clamp any sort of spike when it turns off. But this would normally be up here, and I don't know why they've put it down there, because that's not how you normally use NPN transistors. I'm not sure why they've done that. I would normally have expected that to be on the other side of that transistor, and it would have worked theoretically just as well. It's very strange. I'm not sure why they've used it in that particular way, because they are both 2N5551 NPN transistors rated at a fairly high voltage and a fairly low gain. The only other thing that's worthy of note, and it's significantly worthy of note, is the 2 terminals here. They really are just connected directly across that lithium cell. So when you bridge these two terminals over here, it just shunts out this lithium cell to reset the circuitry. That is a bit severe. They could have done that a different way. They could have actually had a resistor between, in this position here, feeding the circuitry, and then when you bridge that out, that resistor would at least limit the current, because otherwise it's just relying on the internal impedance of the cell. It's a bit naughty, but I guess it's not that critical because it's not going to get used too often, and yeah, it's strange. Very odd. But I'm not sure how accurate the timing is. The only way I'm going to find that out is to set the time and then just, leave it for a while and see what happens. So I'll probably do that. I shall put this back together, set the time, and then we'll see if it drifts. But there we go. It's that's the topology of the, I keep going to call this astrological clock. I mean, it would be good because it could see into the future. But it's an astronomical clock. It sounds strange. It sounds like astronomically expensive. But there we go. It's an interesting device, and it was well worth taking to bits and exploring.